Okay, it looks like the flow of connections is dropping off. Again, thanks for everyone for joining today at our special noontime for our webinar. Dr. Filip Neele has joined us today for a presentation. He has a background in geophysics from, and I'm going to mispronounce this, Utrecht University. He's been active in the field of CCS since 2006 and involved in many projects related to the transport and storage of CO2. Filip coordinates CO2 transport and storage activities in TNO to ensure that these two strongly linked elements of the CCS chain are considered jointly in CCS projects. He's co-chair of the ZEP network technology covering the areas of CO2 transport and storage. Currently, he focuses on storage of CO2 in depleted gas fields involving several developing CCS projects in Europe. And with that, we'll turn it over to Dr. Neele. Thank you.
Thank you, Terry. Can you hear me well?
Yes.
Excellent. So thank you. Thank you for inviting me to do this webinar. So my name is Filip Neele. I'm with TNO in the Netherlands. TNO is the largest R&D organization in our country, in the Netherlands. So in the next 15 slides or so, 40 minutes, I will give you an overview of the work that we have been doing for several CCS consortia in the Netherlands who are looking to develop CCS transport and storage infrastructure in our country, in the offshore area of our country, aiming to use some of the depleted fields that are there for the storage of CO2. So my aim is to give you an impression of the challenges involved in using these depleted fields, these perhaps easy opportunities for storing CO2, and I'll try to convince you that it's actually not that easy to store CO2 safely in a depleted field. In my presentation, I will not go into, for example, the analysis of geomechanical stability of the subsurface, of the reservoir, of faults. I will not really go into, excuse me, integrity of wells, but I'll try to sketch the challenges that are linked to getting the CO2 safely through a pipeline network into wells and into the reservoir. So let's have a look. So depleted fields. I will show a map in a minute to show you that we in the Netherlands have actually quite a lot of them. So, and around this time, this decade, I think the majority of the fields will become sort of empty. They will have reached the end of their lifetime. So they are considered in our country as a prime target to reuse for CO2 store. Of course, they have several advantages. They have a proven trap, a proven seal that has kept natural gas down there for a long time. From the production period, there is an abundance of data that can help understand the response of these fields to repressurization with CO2. The certainty about how much CO2 could be stored in each of those fields is, of course, rather high. It's a matter of computing how much was produced and converting that basically to CO2, and that's it. And if we're lucky, if we are there in time, there is an opportunity to reuse some of the production facilities like pipelines, platforms, and wells. Of course, as always, there are also challenges. fields, producing fields tend to have wells that have been plugged and abandoned some time ago, and if it's a long time ago, there may be a very real challenge there. Sometimes data has been lost because of takeovers, mergers. So legacy wells, they are an issue. The availability of the fields is always a challenge because the end of production tends to be a rather soft target, if you like, strongly dependent on gas price. So the availability of a particular field for CO2 storage is never actually certain until, of course, preparations start. As for reuse of production facilities, there is a limited time window there because of regulations requiring facilities to be removed or plugged and abandoned within a few years after the end of production. So in this presentation, I will go into the challenges that we have identified that mostly arise from the often low or even very low pressure after production. On the map, on the right-hand side, is the North Sea area with the bordering countries. And in red, I've indicated a number of the ongoing CCS projects. There's quite a number of them. Recent years have seen quite an increase in the interest in CCS, and as a result, we now see more than a handful of projects that are designing and will soon be constructing infrastructure to transport and store CO2 from the various industrialized regions around the North Sea. So we have a project in Southern Ireland, there's one in the Bay of Liverpool, there's a few on the east coast of United Kingdom, there is Northern Lights in Norway, and most of these use saline aquifers for storage. Exceptions include the Ervia project in Ireland that is using a large depleted gas field, as well as the Liverpool Bay project, also looking at depleted gas fields. There's the Greensand project in Denmark, offshore Denmark, that's looking at depleted oil fields. And then we have 3 projects in the Netherlands, Aramis, Athos, and CO2 Transport, which is actually a cooperation with Belgium, at the Port of Antwerp. And these are all looking at developing some of the Dutch depleted gas fields for CO2 storage. Also noted as a sort of an exception on this map is the D'Artagnan project in France, which aims to collect CO2 from the Dunkirk region in France and to transport it north to basically one of the storage projects in the North Sea. So if I go to the next slide, I will be zooming in on the Dutch part of the North Sea. So I'll be focusing in on the coast, the Netherlands, the Dutch coast, which is about here. And this is part of the Dutch offshore North Sea region. And what we see is in green, the shapes in green are the gas fields that most of them have been producing for the past few decades. And again, most of them will become depleted in, let's say, midway this decade. What we also see on the map is in green gas transport pipelines that transport the gas to onshore, and a few oil pipelines that connect oil fields in red also to shore. So we have about 100 gas fields that are potentially suitable for CO2 storage, and together they have a storage capacity of about 1 gigaton. So that's great, but then the question is, how should we develop these fields? How do we get the CO2 in the subsurface in a safe way? So there is a timeline of field development which has been estimated to be 5 years at least, and probably more like 7 years between start of activities and actual first CO2 into the reservoir. Of course, there's the ranking of all these fields, which are the better ones, which are the more risky ones, which ones are the provide cheaper options, etc. But then the question that I alluded to, the main question, I think, is how to operate these low pressure fields, how to use the wells that have a very low pressure at the bottom hole, and how do we develop a transport and storage system that links several of these fields to suppliers onshore. To give you an impression of what a CCS network could look like, it could be like this, where we have the Port of Rotterdam down here below at the lower bottom of the map. We have Amsterdam near where Aramis is, where Athos is. And then, let's say by 2035, perhaps, a network in our offshore could look like this, with trunk lines connecting to gas field clusters. This is currently the first one being developed, the P18 cluster. A little bit further offshore, let's say about 40 to 50 kilometers offshore, is what we call the P15 cluster of fields. And then the better fields, as we understand them today, lie further up north. So we have to connect with another trunk line to perhaps this set of fields. And then further up north, there's quite a bunch of fields, and they represent the larger storage capacity. So this could be what is going to be constructed over the next 10 to 20 years. At the moment, the only certain development is enclosed in this square here at the bottom. And on the next slide, I'll further zoom in to this area. And this is where we see the Rotterdam harbor with all of the industry located in this whitish zone. And currently the Portos project, or I should say the Portos consortium, is developing the Portos CCS project, which connects the industry here to this offshore cluster of fields, the P18 fields, that have a storage capacity of about close to 40 megatons. And it's connected to Rotterdam by a high-pressure offshore line and a low-pressure onshore collection network, like here. There will be a compressor near the coastline that converts low pressure into high pressure and then feeds into the CO2 to a platform right here, where there are 3 to 4 injection wells that connect to this storage capacity. The timeline is for financial investment decision, so the decision to go ahead and construct early next year, so as to be able to start injection by 2024. The project, if you like, currently consists of the Portos consortium that is going to do the network and the storage operation, with 4 emitters who will be supplying the CO2, mostly from hydrogen production facilities. There is good support from politics in our country. There is a subsidy in place to make sure that that all of this will have a positive business case. And basically the emitters will get their money basically from the European trading system, plus sort of a contract for difference that guarantees some minimum price for the captured CO2 for a period of 15 years. That's what makes this project work. And currently, as you can see, the project is just about to take financial and investment decision. Permit application for storage in the fields here have been filed or have almost been filed. And today, the detailed studies are being completed in order to propose the transport and storage system to the future suppliers. So this is ongoing, and as I said, there are 2 more consortia that are developing similar networks in our part of the North Sea. They are typically 1 or 2 years behind the Portos development. So let's have a look at how to do this, how to use a depleted gas field for CO2 storage. Let's get down to details right away. Let's go to the interesting stuff and look at the implications basically of the low to sometimes really low pressure in the field after production. So the problem lies in having to bring the CO2 from the high pressure surface transport pipeline to the low pressure in the reservoir. So our reservoirs tend to be at pressures between 10 and 20 bar at depths of 3 to 4 kilometers. This is because the aquifer that is connected to the reservoir is usually small in volume, so pressures tend to remain low after production. You will know that bringing CO2 from high pressure to low pressure will induce a temperature drop, and it's the management of this temperature drop that is causing headaches. So what we're looking at is basically temperature limits in the system. One of them is close to the wellhead, where we have material of the wellhead itself, of the piping, of the uppermost part of the well itself, that need to be at high enough temperatures. So let's assume that temperatures need to be higher than -10 degrees centigrade, just for material properties' sake. Also because we don't want to freeze the annulus, although we could replace fluid by gas in the annulus. Of course, we have also to worry about the reservoir itself and the caprock. We don't want cold CO2 entering the reservoir to bring into peril the reservoir and caprock integrity. So we have to worry about that, but I will not talk about that here. This, of course, needs specific simulations to know when temperatures in the fields are going to pose an issue in this respect. Then we have to also maintain operability of the well and of the reservoir. And in this respect, we're talking about salt deposition and hydrate formation in the well, or perhaps near the well in the reservoir. In this graph here on the right, I'm showing temperature on the horizontal axis, pressure on the vertical, and this area here is generally where conditions are such that CO2 hydrates could form. So in the presence of water, and when conditions are right, hydrates could form that could block the pores or could block the well. In itself, this is not a threat to safe and secure storage and containment, but it does stop you from using the well as an injector. So we have to keep conditions in the well or near the well outside of this gray zone. And as a rough approximation, we can say, based on this graph, that as long as temperatures are above about 15 degrees centigrade, hydrates will not form. Of course, we need water to form hydrates, so in case of a very dry reservoir, this limit might be relaxed a bit. So we now have two temperature limits that I'll be using in the following slides. Of course, there are additional limitations. You cannot inject unlimited at unlimited rates in a well, so there's a limit due to erosion or vibration. But again, we'll not look at that here. So I have two wells for you. The first one is a flow controlled well. So in this case, the well is connected to a pipeline with a mass flow control valve. And you will be wanting to have such a valve, which basically is a means to control the amount of CO2 that flows into a well, because you, in a network with several wells, you will want to have some control over where the CO2 is going. Right, so we have a valve at the top of the well that we can close a little bit. The well is 3,500 meters long. It's about 3.5 kilometers deep. At the wellhead, we will look at mass flow rates between 10 and 170 kilograms per second. Pipeline is at 100 bars, so we have liquid dense phase CO2. The wellhead temperature of the CO2 is 10 degrees centigrade, basically seawater temperature. And at the bottom of the well, we have this depleted field, which is at a low pressure, at a high temperature, and again at this depth, over 3 kilometers. All right, so now we're going to vary the mass flow rate into the well, and this is what we get. So what you see here is a series of profiles that show you temperature on the vertical axis as a function of distance along the well. So the well is actually a little over 4 kilometers long. It's a deviated well. And we see several profiles in here, the thin curves that represent different flow rates. Also indicated on the figure is these two temperature limits that I explained on the previous slide. So we have the -10 at the top of the well, or near the top of the well, and we have the +15 centigrades at the bottom of the well. This is the hydrate related limit. The heavy curve, this thick curve here, represents diameter in the well, so we have a constriction near the bottom, and we have probably the control valve near the top of the well here. So we'll ignore the thick black curve and we'll look at the different profiles. We see that depending on the extent to which the valve is closed, that we get different flow rates and different pressure drops across the valve. So if we close the valve to a large degree, we get a low flow rate, in this case 10 kilograms per second. But because of the fact that the valve is almost closed, there is quite a pressure drop and an associated temperature drop. So we get low temperatures near the top of the well. As we slowly open the valve, we increase flow rates, we increase this minimum temperature until we hit this purplish curve, which is the curve for, in this particular example, 80 kilograms per second, or a little bit over 2 megatons per year equivalent rate, that for which we see a temperature decrease to -10 near the top of the well, after which temperature increases due to pressure increase in the well, and then at the bottom of the well we arrive nicely above 15 degrees centigrade. So an important conclusion from this example is that this particular well actually has a minimum injection rate of over 2 megatons per year. It is to be noted that this was, in its lifetime as a production well, was a very good well. So there was good production rates, and we see that this very good well can be used only if the supply rate can be guaranteed to be quite high. So that's one, I think, very important finding for a well into a depleted field. Let's have a look at the second type of well, which is a well that's always open. So there is a choke or a valve at the top of the well, but in this case, the valve is always open, and we try to regulate flow into the well by changing the conditions in the pipeline. Because decreasing the pipeline pressure will also give us lower rates, and maybe that is a good way to get rid of this problem of high minimum flow rates. So what we see in the graph here on the right-hand side, it's a bit of a complicated graph. What we have on the horizontal axis is mass flow rate. So again, depending on the conditions in the pipeline, we can decrease or increase mass flow rates through the pipeline into the well. And on the vertical axis, we have pressure at the wellhead in blue, that's the blue curves. And we have downhole temperatures in red. These are the red curves. Right, and let's have a look at mass flow rate of 60 kilograms per second. Let's say a little below 2 megatons on a yearly basis. What we see is to reach 60 kilograms per second, we can do this when the CO2 in the pipeline has different pressures or temperatures. This curve here is for CO2 temperatures at the wellhead of 60 degrees. This one is 40, 20, and 10. And we see that if we have CO2 at a temperature of 10 degrees, which is, again, let's say seawater temperature, the pressure at the wellhead is 50 bar. What we see for that particular condition in the pipeline we see that the downhole temperature is below 15 degrees. So this, in fact, is not a feasible solution. This means that these conditions all have downhole temperatures below 15 degrees. So for this particular well, we cannot inject at 60 kilograms per second with this setup. And this agrees, by the way, with the previous slide. What we see, if we summarize this graph, is that we get two green areas that lead to, if you like, admissible conditions in the well, or at the bottom of the well near the well in the reservoir. And these are for mass flow rates of 0 to, let's say, 25 kilograms per second, a little below 1 megatons per year. Or if we turn up the system, we could use this well to inject safely at rates close to, well, 70, 75 kilograms per second or up. So for this setup, for this way of using the well, we get a flow rate window, an operational window that is made up of two parts, two separate parts, separated from each other in the middle, perhaps. So this tells us that the two ways I think that one would like to use CO2 injection wells, either in a controlled sense or in an uncontrolled sense in some way, they pose different problems. They pose different challenges. And this summarizes what I've just tried to explain. So this was all talking about steady state conditions, and I did show to you in the previous two slides that there are conditions in the system that we can define in which we get feasible or admissible conditions in the system for steady state conditions. Now, of course, the wells need to be started. Every now and then they need to be shut in. And these transient operations will also cause fluctuations in temperature. And these examples on this slide are for a similar well, and they will show you what happens during brief periods of time, but show you what happens as far as temperature in the well is concerned. This graph here, on the left in the middle of this slide, shows you what happens as an operating well is shut in, and it will show you the amount of liquid that is formed along the well. So we have again a long well distance up to almost 4,500 meters on the horizontal axis, and when I click my mouse, you will see profiles springing up that represent different steps in time, and the entire sequence, I think, represents 1 hour or something similar. So this is what happens. You see that a little bit of liquid is formed inside the well, but this is not a problem because the liquid will sink to the bottom and will not affect any parts of the transport system. This graph in the upper right-hand side so shows temperature along the well, same well, a long well distance on the horizontal, temperature on the vertical. And when I click my mouse, you will see profiles coming up that over the course of, let's say, tens of minutes or an hour will show how the temperature evolves and slowly reaches an equilibrium with temperatures close to zero. It's the 10 degrees that I was talking about, increasing to eventually reservoir temperature, which was 120 or close to that at the bottom of the well. We also see that during this brief period of time, strongly negative, below zero, freezing temperatures occur in the well. Now, whether this is a problem or not should be simulated, should be found out by simulating the entire well system with all of the elements, all of the cement, liners, casings, formation, and computing the heat transfer during that short period of time. I think such calculations show that these low temperatures do not really go far beyond the first steel wall, the tubing wall. The annulus fluid actually acts as a very effective insulator. What we see in the bottom graph here is, let me check for time, is the temperature as it starts off here. It will move at the bottom, at the top of the well, it will move to the phase line, it will drop and will then arrive at the 10 degrees. I see that my time is running out. I will quickly go to the next slide, which is an example of that goes into the question of how does it work? How does this work out in networks? So here we have a sketch of a situation with 3 platforms. This is a pipeline that connects to shore, 2 inter-platform pipelines, and these 3 platforms have the wells that we see in this graph here, and indicated are for each well minimum and maximum flow rates derived along the lines that I just explained. So these are all high quality wells during their lifetime as producers. And we see that several of them have these high minimum flow rates that I was talking about. So anything below, let's say, 1 megaton on a yearly basis cannot be injected in these wells. It cannot really be injected in these wells. And if the flow rate becomes really low, then the operator of a network that is shown here, this simple network, if it drops to below 10 kilograms per second, this entire network has to be shut in. So the operator of this particular network, even though he needs very few wells to run a network at an industrial scale, there are limits to the flexibility of this network. I'll skip this. A few words about this one. I've talked about minimum and maximum flow rates for CO2 injector wells, and we find that quite obviously the tubing is an important parameter because it controls pressure increase or pressure drop between the top and the bottom of the well. So the tubing is actually a parameter that the operator can use in the design of each well, and following from that, in the design of the overall injection window of the entire network. So you can, and furthermore, you can think of downhole orifices that could be used to advantage. Pipeline pressure is an obvious parameter. CO2 temperature is a parameter. And here perhaps it's interesting to note that the Portos project that I mentioned previously is going to use warm CO2 in gaseous phase during the first years of injection to overcome the limits of low reservoir pressure, while at the same time reaching let's say, interesting injection rates and maintaining operational flexibility. And then as the reservoir pressure in the fields becomes high enough, the pipeline and the wells and the reservoir, if you like, will be switched over to high pressure. CO2 will be converting from gas phase to liquid phase to make use of the higher rates that are inherently associated with liquid CO2 transport. After this first rather difficult first phase. Also in this table is injectivity. It's a parameter. So as I said, good producing wells might be a problem when converted as is, if you like, to CO2 injectors. You might like to reduce the injectivity somewhat in order to manage the operational window of the well. Annulus fluids could be used to allow lower temperatures in the well, or of course a combination of all of the above. I see that my time is running out. I had some more material that talks about further interesting limits, but I'll skip all that. I'll give you some further reading. Of course, the presentation will be made available to you. And with that, I thank you for your attention.
Thank you. Anyone having questions can enter them in the chat, or they can unmute and ask.
Hello.
Thanks, Julia.
Philip, this is Sriram. I have a question.
Yep.
I was wondering, most of the discussion here centered around the CO2 after it reaches the wellhead. And you just made a reference, an oblique reference at some point now. I was wondering, what is the state of CO2 as it is transported in the pipeline? Is it a supercritical fluid or is it a liquid?
So as I said, for the Portos project, it will be in the first few years of the project, the CO2 in the pipeline will be in gas phase. Once the reservoir pressure is high enough, they will convert to liquid phase. And I'm saying liquid rather than supercritical because even though the pressure in the pipeline is expected to be higher than 80 bar, the temperature, I think, will be probably when it reaches the platform closer to seawater temperature, then above about 30 degrees centigrade. So technically, I think the CO2 will be a liquid. Now, if I may, this approach by the Portos project, gas first, liquid later, can only be used because they use an insulated pipeline to bring some of the compression heat to the platform. All of our other interesting gas fields are located further offshore, further from the shoreline, and those other, the other projects, Athos and Aramis, they will probably be transporting liquid CO2 from the very start. So they'll have to find a solution, and that's ongoing work. They have to find a solution to these difficult first phases when reservoir pressure is still low.
I see. If I may ask a follow-up question.
Yeah.
In general, then, isn't supercritical CO2 the mode of choice for transport in pipelines? Because I started looking into this for a project we are doing here at LANL, and many of the research seems to suggest that they always seem to say that supercritical CO2 is the best because it has lower viscosity, it's like a liquid, and only thing is you have to keep it above its critical temperature and pressure. So
Yes.
in general, apart from the Portos project, for the other projects, is that the norm, or is liquid CO2 the norm for transport in pipelines?
Yes, I think it's going to be liquid. So I think, and I'm giving you the view from, let's say, the North Sea region here. The projects currently developing around the North Sea that are, they are mostly looking at storage options quite far from the coastline. So pipelines are long, let's say 50 to 100 kilometers. And while the CO2 close to shore might be at a pressure above 73 or 75 or perhaps 80 bar, and above the critical temperature, I think quite soon the CO2 will reach sea temperature.
Okay.
So, and then you're talking liquid, right?
Yes, that's true. I see.
So that's what we're looking at here.
Thank you.
And I think Neeraj is confirming this. Thanks.
Filip, do you mind follow-up question?
Sure.
So since in the pipeline, the CO2 has to go through the transition from supercritical to a liquid, are there any challenges associated with this transition? Anything related to modeling of this process, or anything related to the flow?
To the best of my knowledge, I would say no. Because when moving from supercritical conditions, perhaps near the coast, when the CO2 is still perhaps a little bit warm from compression, to liquid conditions further out, there is no phase change. It's a gradual change from supercritical to liquid. There's no phase line that is crossed. So I don't think there are limitations or issues with simulating that. So yeah, we're not worried there.
Filip,
Thank you.
this is Neeraj Gupta. I have a question on the depleted reservoirs overall. Did you see, it seems like there's a design and engineering issues that can be probably solved at some cost. But did you see any showstoppers that would limit the use of depleted fields for long-term storage?
Not yet. That's not to say that I expect to find one tomorrow. What we did find is that as you dig deeper, like we have done with the Portos Consortium, as you dig deeper and start looking at first steady state scenarios, you find issues. You solve them by going into these safe domains. Then you have to go to the next layer, which is that of transients. And there you find new issues. So what we found is that by adding detail, we have kept finding new challenges. And up to now, we have found solutions for them. I think the fact that the Portos project is now preparing itself for FID means that everyone is sufficiently confident that the system can be designed and constructed and operated safely. it is going to be a matter of careful management, careful choice and definition of injection procedures, and careful, adapting the procedures to the evolving conditions in the system. But I'm confident that it can be done. It's just that, yes, I'm still amazed by the findings that this seemingly simple and obvious storage option actually turns out to be a rather difficult one. As yet not an impossible one, but it's a difficult one.
Yeah, we have seen phase changes also in our projects, but generally they have been manageable in the field, including hydrate formation. So let's see, it's an important area. Are you looking at EGR also with this enhanced gas recovery, or mainly a storage option?
Projects are now entirely storage projects. I think adding EGR to the mix, we as CCS community in Europe, I perhaps should add, would run into public acceptance issues. So that's not what we want, of course. And secondly, we have looked at the feasibility, or perhaps the economic viability of EGR, and I think it's fair to state that there is none. Most of the fields are depleted to 90-95%, and there just isn't enough gas left to pay for the additional activities, if you like. It's too expensive. Yeah. Thanks. Any other questions? Yes, I do agree with the remark about onshore pipelines. But offshore, yeah, we're in Europe, certainly Northwest Europe, we are talking about offshore systems, since onshore is, well, to put it optimistically, it's temporized, if that's a word. It's not approved for now, so everything is developed for offshore use, offshore storage. And then we're talking sea temperature. Any other comments?
Hey, Philip. This is Sarah Leung. Quick question for you. Apologies that I joined in a bit late, so you might have said or spoken to this, and I might have missed it earlier. But question about induced seismicity concerns. I've seen a recent Stanford study, saying that oil reservoirs should be targeted for carbon storage. Which is a very interesting study in West Texas here onshore, and with thoughts about induced seismicity in some parts of onshore Netherlands. Can you provide just in general any thoughts on induced seismicity, and as it relates to storage in depleted oil and gas reservoirs versus saline aquifers, and just your stance, or just your viewpoint on that from a European perspective?
Yeah, so I've had two remarks on your question, Sarah. So the first one is the stability of faults that are at the boundary of gas fields. So most of our gas fields are fault blocks, and we see that the stability of these bounding faults actually increases as you repressurize the system. So that's good. That's good. Same is true, I think, for the integrity of the caprock. However, some of the gas fields have intra-field faults, and those are a risk, and they need to be monitored. They need to be kept safe, because the low temperature of the CO2 as it enters the field, and in the example I've shown, temperature contrast between the CO2 and the temperature of the field is over 100 degrees centigrade. If you get temperature contrasts like that close to a fault inside the gas field, there may be a chance of activating the fault. So, and this is actually the case for one of the fields that are going to be used by the Portos project. A key risk there is the stability of such faults. I think that's quite different from the situation in saline aquifers, where you do not have the low temperatures of the CO2 when it enters a reservoir, and you have less worry about the temperature-induced instabilities. In those cases, you merely have to worry about the effect of overpressure. Is that answer to your question?
Yeah, that's helpful. I also put a link to the study mentioned in the chat for anyone who is
Thanks.
who is curious. But that helped. Thank you, Philip.
All right, and I think we're about at the conclusion of our hour. And I'd like to thank you for your presentation. We appreciate it very much. And thanks for those attendees. Our next webinar will be 2 weeks from today. There will not be one next week. So look forward to seeing you then.
Yeah, thank you all for your attention and participation in the webinar. It was a pleasure to do, and hope to see some of you at least in the future in person.